Good morning, everyone. I'd like to welcome you to the 17th Annual HPCAIC Swiss Conference. I'm Brian Sparks of the HPCAIC Advisory Council, and with me, as always, is Hussein Harake from CSCS.
Good morning, everybody. Welcome. It's a pleasure to see you here in Locarno. I think this is the first time for us in this location.
At least this building, second time in Locarno.
Yeah, in this building, and I hope that you like it. It's the weather is nice. I think we are almost summer.
The weather's fantastic, although I did see the forecast of today and tomorrow, maybe a little bit of rain, but it'll only rain when you're outside.
You need to check Meteo
Inside
Swiss.
it won't rain.
You need to check Meteo Swiss. This local stuff. So anyway, good morning, everybody. It's a pleasure really to have you here. This year we introduced the tutorial for the first time, and we're happy a lot about it yesterday. We had a good feedback from many people. And this is something that we are looking to move forward with it. I think we would like to, the first thing maybe to thank our sponsor.
Yeah, we have a record number of sponsors this year, so thank you, all of them. One of the things that we did a little different this year was to extend the breaks a little bit. So each break is going to be 20 minutes. Apart from lunch, that's a whole hour. So it'll give you enough time to be able to at least get a cup of coffee, a little bit of bite to eat, talk with each other, talk with our sponsors. They're here for you. They were here for us. So please visit them when you have a moment. They would be grateful. We'd be grateful. But definitely talk to each other. That's one of the big parts of this conference, is just to have enough time to be able to just, commingle. And that brings us to the Wednesday night event that's going to happen that maybe Hussein wants to quickly talk about.
But before the evening event, I would like to share about the number of registration we had this year, actually. And we had a record number. So we were very close to hit the 200 people joining this event, and going back and looking at the back in the time, we were roughly going between 70 and 80, and little by little it's growing, this community, and which is also great for us to see that. For the evening event, it's going to be around 20 minutes from here walking. So we checked, as mentioned, the Meteo Swiss sounds like it's going to be nice during evening, so a bit cloudy in the morning, but that will be improved in the late afternoon. So I think after a couple of days of sitting and eating, I think just having a walk for 20 minutes won't be just like a bad idea. So we will leave here 6:30, which will take us 20 minutes. We'll be almost there at 7. That's where we'll start, actually.
So that brings us today, and we have a full schedule lined up. Tomorrow, you'll notice there'll be a little bit of change in the agenda. We are going to start at 9 o'clock instead of 9:30. We were able to get a speaker from CHPC, South Africa, to be able to dial in and talk to us. So that's why we've brought it in a half an hour. But Thursday, I do believe it's going to be a 9:30 start time, which is great because after an evening event, you kind of need a little bit of later start time. So with that, I'll turn it over to you, Hussein.
Yeah. Okay. So I think today we will. Before we start with our keynote, I would like to introduce Professor Thomas Schulthess. He's he's professor at ETH and he's director of CSCS, and he will just give the first talk. So please join me to welcome Thomas.
Well, thank you. Good morning, and thank you for putting this together. And this means also everybody coming here. I feel like completely perplexed. This used to be a very cozy workshop in Lugano. Even 2 years ago, it was still cozy, and now it's turned into a big conference. And so I very much appreciate, and I'm going to be here all 3 days. So I know there's lots of people who send me emails about talking, and my schedule is going to be rather informal. So I hope to catch as many as possible. Hussein asked me to give me a bit of an overview of where we are. You will hear a lot from us during this conference. I will try to point out some of these presentations. I am going to try to show that in this discourse around sovereign AI, which plays a very important role right now. I know in Europe, but also in Switzerland, we have many discussions. My main argument will be that we're actually well on track to actually having sovereign AI in Europe and in Switzerland. We just need to realize this and invest in the right things. And I hope to start this discussion and motivate some of the presentations that will come during the conference, the great program that we have put together. So there are, I guess, known dimensions of sovereign AI. We're talking about infrastructure, where a lot is being discussed around controlling data centers, hardware and software. So I will preach about software in this in the next 20 minutes, and you will hear a lot about that during the presentations in the next few days. Then, of course, there is data, which is storage, but then also processing and training that have to abide by the ruling law. Now, this is sometimes a discussion on what is the ruling law, and as an American, I can say this, we need to remind ourselves of this point as well. But from a European or Swiss point of view, I think it's also clear that we have to look at what is, in our culture, what are the values that are not necessarily the same everywhere, and we need to respect them. And then, of course, the sovereignty of the model development and training and local AI. I put the local into models into parentheses or quotes, because local doesn't really mean local like when you're in a small country like Switzerland. Local may sometimes be too local, and you have to have a bit more of an international view. And then, of course, we want operational control. So we will be circling around, or these are the topics we're circling around. And what I try to show now is that with where we have taken supercomputing, that started in science, we're already in the middle of this discussion. For us, of course, we've been developing since a few decades the center. The current infrastructure we are discussing was announced in spring 2021, so 5 years ago. We are still building it, but we're getting very close to full completion of the work plan that we agreed on a few years ago, or back in 2019. The center was really around the launch of the GH200 project of NVIDIA, and by 2024, so 2 or 3 years later, ALPS was installed in Lugano, and which we are very close by. The geopolitical situation around power stability of the grid in Switzerland and so also forced us to create a redundant deployment in Lausanne. So ALPS is actually here in Zurich, in Lugano, in Lausanne, and part of it is also at ECMWF, where we have installed a data cube that is close to the data of the European Center for Mid-Range Weather Forecasting, so has access to operational data and to the archive, and then is linked over a dedicated link to the Alps infrastructure here in Lugano, or close by in Lugano. The infrastructure itself builds on this CRAE system management software and the Slingshot network, a network that is partitionable, and then is we have added a lot of software infrastructure on top of this in order to create then an infrastructure that can be split into different platforms that can be specialized to the different communities, including the AI community. And so whatever we are talking about AI now, and what you will hear later today, it was not planned, but we had the ability to react and to accommodate new developments. You will hear, for example, one of the important components to do this, as we all know today, are containers, and we have the Sarus container suite. I believe there is a talk tomorrow in the program describing of what's going on in that area. Actually, there are two talks. There is a keynote tomorrow morning from Thorsten Höfler's group that talks about this acceleration as a service. Now, the platforms is really, they are immersed in the business that we do, namely high-performance computing. We used to have PITSTINT as our flagship infrastructure, and we have a number of experimental platforms. We have Meteo Swiss, I will come back to this, and we have a climate initiative and the AI Center. And the AI Centers, the AI initiative, one of its achievements in the last couple of years was to bring forward Apertus. I will not say much. I think Imanol, I hope, is here. He will give a presentation later tomorrow. All I will say here is a slide that Jonathan loaned me. It's basically it shows when we started 2 years ago and then installed also Alps, etc., and we got started roughly a year ago. The upper graph that you see is the throughput, tokens per second and GPU that we were achieving at that time. And then by probably around May timeframe, that's then the lower graph, and I can tell you there is a lot of work, not just AI training work, but a lot of engineering work that went into the infrastructure to get to a place where we could train the model for about 3 months on about 4,000 GPUs. And to anybody in your HPC who wants to follow up on this, there's a lot we can talk about on how to get to that point. But this is not the only thing that was happening at the same time on the climate platform. We had a simulation using this ICON model that is being developed jointly between the German Max Planck Institute for Meteorology, the German Weather Service, Meteo Swiss, and then us at ETH, C2SM, and CSCS. And here again, this is simulation software, so this is traditional simulations. We know that weather forecasting is based on data assimilation, and there is no forecast without having, the model trained or it's not trained in the neural network, but fitted to the data to be able to predict what is happening in the next days. And so it turns out that this model a high-resolution version of this model that was enabled here in Switzerland with Meteo Swiss. You see the mountains that we have around here and why we need to go to these high resolutions just to get the orography correct. And if you don't get that correct, you can't do any forecast. At the same time, there was this development in Europe going on with ECMWF, creating what is known as the European model, IFS, in the US, using IFS and reanalysis data from IFS to create what they now call AIFS, the AI integrated forecasting system, and which has gone operational last year. And so this is the global picture that I'm showing. And then you see a small square over the Alpine region where Meteo Swiss has been doing their own reanalysis on a high resolution model using ICON, and then developing this jointly with their colleagues, this AI suite to do kind of a fine-tuning of the of this global AIFS onto the local data that was trained over the Alpine region. And it's very impressive, like AIFS is impressive in itself, but they are gaining in skill about 24 hours, so 1 day in the forecast, which normally would take about 10 years to reach such an advance. Now, it's not clear that these advancements, this is really an acceleration or whether it is a one-time jump, but it is a very impressive thing that will have a lot of implications. Mostly, I think, where I see the advantages is on how weather forecasting products are being delivered to the end customer. So not just to us who are looking up the app on Meteo Swiss, whether it rains or not, but actually to the energy companies or air traffic control, etc. So we have a roadmap that by roughly 28, so in 2 years from now, we should have all this also operational. And my main point, going back to this question of sovereignty, in this area of weather forecasting, we had sovereignty for a long time based on the excellent work that Meteo Swiss in Switzerland and its partners in Europe and ECMWF have been doing now for several decades. They reacted very fast, and like I said, they made a model operational, an AI model operational last year. And then there is this Anemoy consortium that is doing these local high-resolution fine-tuning in different areas. So Norway, over the Alpine region, different places in Europe. And I think this is an example where that really shows how good work over decades on data, on modeling, and understanding what you're doing in AI leads to a success. Now, Alps, like I said, is fully productive now, and it is stabilized and I think working very well. This was not a straightforward path to come here. And I will now come to the last point. Namely, we started, like I mentioned, in 2019. We had the first implementation of this gray system management software that turned out to be less microservices and more monolithic. monolithic because when you give a supercomputing company a new idea, they will initially give you what they know how to implement, and that is traditional supercomputers. The first version of this was delivered in 2020, and we have been working, and this is where a lot of kudos to HPE, who acquired Cray. We've been working now since probably 5-6 years to back out of a lot of, maybe not so ideal design decisions that were made in the beginning, and we are, and they have stayed with us. So Alps would not be where it is today if it hadn't been for this commitment to really follow through and develop the software to a point where today I think we can operate the system in this diverse way as I showed, but in a very stable way. And also at CSCS, given this situation, okay, we had the pandemic in the middle and that was not helpful, but there was also some questioning, why are we going this way? And it really required also to do a transformation at our center. And what we have today is something that works, but we have also a challenge, namely economically it's very difficult to sustain this software infrastructure that Cray had developed and that we had to complete the engineering for. And I think we are caught somehow in an innovator's dilemma in that the bigger community out there doesn't really appreciate these investments and developments, yet at some point when it works, the community will switch and will not care anymore about the things that were done in the past. Fortunately, we are not the only ones in this boat. We have partners, and we will hear, we had a tutorial yesterday. Unfortunately, I was elsewhere. I couldn't really talk to Alex, but Alex is here, I suppose. He will give a talk later. So we had partners like Los Alamos, NERSC. There are a number of partners who had invested in this vision of Cray and Los Alamos, NERSC, us, and then also Bristol. Sadaf, who used to be here, Alam, she moved to Bristol. We got together about 3 years ago, and together with HPE created this consortium we call Open Composable Heterogeneous Adaptable Management Infrastructure, and Open Chami, and as to create this as now a fully open, also open governance way to do the system management infrastructure development. And you can say, well, yet another operating system, yet another system to manage the infrastructure. I think this is the first one that is really fully open in the sense that unlike just open source is paying a lot of attention also on the governance of this infrastructure, something we need to learn in other places as well. It is governed under or part of the High Performance Software Foundation, which is organized within the Linux Foundation, and probably one of the best outcomes, I would say, of the US exascale computing project that developed a lot of software and is the legacy of this ECP is going into this foundation and is going continuing to live on. Dell has joined the consortium. NERSC 10, I believe, will be deployed under this software management infrastructure. Los Alamos is the plan of record is to move all their systems to OpenCharmy this year, and we are planning a year from now in Q1 2027 to move Alps under this as well. So when we now look at what has all happened, I can say, as far as I'm concerned, supercomputing infrastructures they exist here, they are under our control. We can train models, like I said, you will hear a lot more later today, and we are well on our way to sovereign AI. In some areas, like in the climate weather domain, I think we're already there. What is important is that we remember and invest in things that we can sustain. And I want to underline again, we can sustain, if we want, the development of open source software and open models. And we can sustain on data. I think the reality is, and the example of ECMWF and the weather services show, on data we have to collaborate. And the same, I think, is true for large language models and other parts of AI. And on infrastructure, we will have to collaborate. Simply building something like Alps today, with all the craziness in the market, would be very difficult for Switzerland to do alone. But I'm sure together with other countries in Europe, but I'm also convinced other countries like we collaborate with Singapore, Korea, with other places in the world, also in the US, we can maintain infrastructures like this. So I hope I have opened the discussion with this. I look forward to having more debates during the conference, and I really hope you will all enjoy the next few days. And thank you for putting this together.
Thank you.
So,
any question?
okay.
Thank you. Just a comment on OpenCami and the open source software in the field of management. There is probably a little misconception that this is a new approach with open source system management in clustering field, because ClueStar is like 7-8-year-old solution, already fully open sourced, covering a lot of stuff in managing HPC clusters and so on. But OpenCami is really way back behind. So, and it's also sovereign, it's a European product, fully open source, as I said. So might be possible maybe to reconsider. Maybe I'm not trying to make marketing, but it's just putting data. There is not like a very new thing here. It already exists, and maybe worthwhile to looking at it.
Yeah.
Okay, thank you.
So I think what I want, and this is now an important point, when I speak about open source, and particularly in the context of this, the high performance software foundation, there are many, even CSM is open source, so they are released under an open license. What I mean, and for an open source project to be complete, and this is really where that doesn't apply just to system management, but to any form of open source software, is that it is owned by the community, that there is an open governance, and it's for example, just when we say it's a European project, we have learned the hard way in Switzerland that we are not in Europe, okay? So it is important that we leave this thing behind us and really open the governance of these projects and get adoption. And that's why and that's how actually we can have a guarantee, and we learned it from Linux, decades ago, that, this is how the community owns the software. And that's what I mean with open source. And we will hear now, I think, from Erik, who is known as the Mr. GROMACS, or he has been leading the development of GROMACS as a software he will talk about, and also will talk about the adoption of AI in this domain. Erik is a professor at KTH University and is also the director of the NICE, so Erik, correct me if I'm wrong, the National Academic Infrastructure for Supercomputing in Sweden, which is also another very encouraging development, and we have been collaborating for many years. So Erik, if I may ask
Thank you, Thomas.
Sorry, I was not clear.
I think,
Hussein said I should introduce.
Yeah, so I think Thomas introduced Erik, and this is great also. So please join us to welcome Erik Lindahl from the University of KI.
I like it when other people do my job. It's great. Keeps, I'm really tired from last night. No sleep, so that was helpful.
Thank you so much. It's always scary when they move your presentation to a new computer, but if we're lucky, some slides might actually work here. It's great to be here, and as Thomas said, that in one way, my job in Sweden is really easy because I just copy everything Switzerland did 10 years ago, and people think that I'm a genius. So we are very inspired by Switzerland. But when Hussein and Brian and others asked me to give a talk here, it's also, much of my history is actually focused on my group's research. So I'm going to give you a story that kind of starts from simulations, then ends up in AI. Between the lines here, and actually explicitly in some slides at the end, I think there are going to be some lessons, maybe not so much about infrastructure, but in particular about software, where we're taking the usage of these computers, and likely, I think there are some common trees to success stories. Whether GROMACS is one of them is up to others to decide. But I'm actually going to start. This is scary in one way. I built my entire career on molecular dynamics simulations, and it has served me well. And I'm both insanely amazed with AI, and I'm also scared, because this is likely going to undo everything I've done for a quarter of a century. Now, when faced with that, you can choose to keep being scared and worry as somebody else is eating your lunch, or realize that it's happening and try to join the train. And I decided to go for the latter. But just as for supercomputers, as fun as computers are, the reason taxpayers are paying for this is that it's important. These happen to be proteins. It's one of the first ever proteins where I actually determined the structure in my own team. We actually have an experimental branch nowadays. These are not any random structures. They're super important proteins that sit in our nerve systems. Why is this important? Well, one of the most important applications of this has to do with anesthesia and understanding consciousness. So this is a real quote from Fanny Burley that underwent a mastectomy, so removing her uterus in September 1811. And in those days, we didn't have anesthesia. So she actually lived to survive this and tell the story. But can you imagine going through a major surgery and surgeons cutting and tying without any anesthetics whatsoever? So there are miracles of modern brain surgery, heart transplant, everything. The only reason why this works is that you can actually sedate the patient so that they're not screaming on the table. It used to be that a good surgeon was a fast surgeon. This only works because of anesthetics. Anesthetics started around 150 years ago, and you can actually visit the Morton Auditorium in Massachusetts General Hospital. This was in 1846, the tooth extraction. At those times, you use ether. Ether is really good at sedating patients. If you're really lucky, you can revive them again. And much of the modern development of anesthetics has really been able to develop better molecules that allows you to revive the patients reliably, so that you have much broader so-called therapeutic windows. And that's kind of as much background as I'm going to tell you. The reason why this works, and we know that today, is that your nerve signals works by molecules, electrical signals being conducted in nerves. When they reach the end of a nerve cell, these molecules release neurotransmitters that diffuse over 10 micrometers or so. And then there are these receiving transmitters in the next nerve cell that decide whether you're going to create or cancel a nerve signal in the next nerve cell. And what all these various compounds do is that they selectively either block or increase the response in these nerves. You can actually, you're going to help us do a scientific test of this tomorrow when you have a glass of wine at the joint dinner reception, because that alcohol molecules will directly influence these receptors and thereby change your brain's behavior. The way you measure this, some details in gating, and that you can measure the currents in these channels, and I'm not going to go through all the biology here, but the reason why these currents happen is that the molecules in this case, they undergo different conformational transitions, so they move between different states. And typically, there are at least two open and closed, and sometimes there's a third desensitized one. And what's happened with computers the last few years is that computers have gotten so fast that we can simulate these transitions, which are really cool, because in the lab, I can measure them, but I can really, determining the structure of this is virtually impossible. I can determine the structures of the closed one, but capturing these transient open states are virtually impossible. And it's in these open states that the drugs, both anesthetics and alcohol, bind. And that now brings us over to the computational side of this. I spent the last 25 years of my career developing the tools to do this, in particular classical molecular dynamics, as Warshall, Levitt, and Karpus got the Nobel Prize for some 10 years ago. This is a trivial method in many ways. The interaction between two atoms is completely independent of the interactions between two other atoms. And then it's just a matter of compute these interactions many times and then update them quickly, and then try to take a billion or a trillion or a quadrillion steps. Now that takes a time even on ALPS. And the problem is that these problems are entirely limited by sampling. Ideally, you would like to do this with quantum chemistry, but that's completely out of the question, far too expensive. So arguably what I spent, this sounds scary, that what I spent at least a decade of my life on was just looking at those very expensive non-bonded interactions and try to optimize them. At first we used, the multimedia extensions on CPUs designed to compute shadows on MMX registers originally. And then you kept basically iterating and trying to squeeze out every single floating point operation we could of the hardware, while also removing every single floating point operation from the equations that you could buy on it. I think the peak here was IA64, which is a completely horrible hardware in every other sense. But there I reached 99.4% of the theoretical floating point of the hardware. But this was when I was a postdoc at Stanford. And at the time, there was this crazy group led by Pat Hanrahan, professor of computer science, completely uninterested in any commercial applications, just interested in the base science. He had this idea that you might be able to use streaming processors. And they had a broad project of developing their own streaming processor. And funnily enough, there were these companies on the market that had architectures that were almost streaming processors. In particular, the local, a local company, ATI. So he had two students sitting and doing kernels of these. And one of these poor students had to work with me. So the poor student spent 2 years trying to get GROMACS to run on one of these. We didn't even have proper 16-bit floating point at the time. And no kernel could be more than 1,000 instructions. Fixed length. And this student, after 2 years, the student finally got this code running, and it was only a factor 80 slower than running on the CPU. So you would forgive the student for basically deciding that this was not the future. He actually managed to complete, I think this was in 2002, it took him another 4 years to complete that, finally write up a thesis. Apparently got a job at some local startup. No, so Ian has done pretty well at NVIDIA since, but I keep teasing him that his first ever simulations were run on AMD hardware. Now, why did this work? Actually, the whole point, it didn't work. It was a factor 80 slower to start. But the reason why this worked is that NVIDIA, Ian, many other people, they kept pushing. So a few years later, we got proper 32-bit floating point. They got rid of the limitations of the number of instructions in the kernels. They kept pushing the performance. I think we worked probably 10 years with them before this became not just competitive, but the obvious better way to do it. So in hindsight, it's very easy to see that it wasn't obvious. This was not at all obvious at the time. And there were probably 20 occasions during the time where any reasonable person should have given up. While NVIDIA in particular, they believed in CUDA and they kept investing. But I also remember, and it's probably the NDA has probably long since expired, that we had many of these meetings where they kept arguing that they can't support these esoteric platforms that only 1% of their user base is interested in, such as asking to have a proper profiler on Linux, because 99% of the market at the time was Windows. On our side, I think the reason why we were successful is that we didn't try to optimize code for GPUs, because we realized that if you're in factor 80 behind, there is no way this is going to work by trying to tune some instructions. And what worries me a bit, and this is not to boast about Gromex, but I think I see too many groups trying to take their CPU code and just port it over to the GPU. And it might work short term, but you're never going to get those orders of magnitude performance improvements. So I wish I could take credit for this, but I have a really smart colleague who's a mathematician and some very, very smart postdocs. And they decided, rather than just trying to squeeze out more floating point operations, they went back and revisited some of these algorithms that are 45 years old in our field. Had you asked me 20 years ago if there was one algorithm that would never, ever change, I would have said it's going to be this linked cell algorithm of Verlet, how we create neighbor lists. And we completely threw it out the window. Because my entire idea that we need to optimize floating points is completely wrong on GPUs. Optimize the memory, make sure that you keep the GPU fed instead. So the reason why we were successful is not that we're good at coding CUDA, but we were willing to go back and revisit our algorithms. And once we had revisited those algorithms, everything else was more or less a free lunch. So GPUs are basically an infinite amount of flops. The only problem is that this then required us to rewrite all our kernels. And these new kernels are then going to be hopeless for the CPUs. Or at least so we thought. Funny thing, if you look at a modern CPU, it kind of looks like a GPU. So I used to be able to get 1% performance improvement on my CPU. When we just ported the GPU kernels over to the CPU, we gained 25%. So since then, we have transferred everything we do to a common general algorithmic way of calculating and adapting this to the hardware. And I'm not going to go into too much details here, but if you see here, the way we would do it classically is load one element at a time. That's a memory operation, and each black dot here is a computation. This is fine, but basically for every calculation, we're doing one load operation. While on GPUs in particular, we do one load operation in parallel, load 4 elements, but then we effectively do 16 floating point operations. And that means that you can exploit this almost infinite amount of floating point operations on the GPUs. And then today we support this basically for anything, including your toaster. What this then enabled us to do is that we basically took one algorithm at a time. We started with the non-bonded forces, and then when the non-bonded forces had been moved over to the GPUs, we'd move in over 90% of the flops. But that just meant that we're now, the new performance bottleneck is not the previous 90%, because they're executing on the GPU and they're done in a pinch. Now the particle mesh eval, the long-range electrostatics Fourier transforms, it used to be 5 or 10% of our runtime. Now that is 90% of our runtime. And then you have to move over that algorithm, and that basically goes this way, one algorithm at a time. I'm more than happy to share details with you about, but it's not the details of the algorithms that's important here. This probably took us 4 years. Every single one of those colored is a major project, possibly for one PhD thesis. And somewhere there, we were pretty happy. The only problem is that we started to see these very nice XE-DGX machines with 4 or 8 GPUs. Now, that's in principle fine and dandy. The only problem is that when we started to try to communicate between GPUs, we realized everything we'd done in communication was done for traditional MPI clusters or so. And the second we went outside one GPU, performance, the scaling just didn't work. Thank God we had some really good long-term company from NVIDIA here. So they put 2 engineers who worked with us, and I'm so sorry because I think we kept abusing them for 6 years, saying this is not good enough, we're not going to accept hacks. But NVIDIA has been really good about becoming part of the team and engaging in this long-term. So they basically helped us rewrite everything we do in communication. And again, not just taking the CPU code and port it over, but think about the architectures today, the long-time direction where things are moving, and completely redesign how we're communicating between GPUs. And in particular, that means that we initially saw the GPU as an offloading device, but now we're starting to do communication directly between GPUs, which again, today is obvious, but 5 years ago, the amount of bugs in these libraries was insane. Doing direct Fourier transforms directly between the GPUs. NVIDIA spent 2 years optimizing small 3D Fourier transforms for us because everything is dominated by latency, while their entire hardware is optimized for throughput. Even then, we had problems because again, we keep using both the CPU and the GPU, which at the time, everyone told you don't do that. But NVIDIA kept telling us, don't worry too much about it. There's going to be a bright future when you will be able to use both types of devices. And we see that with Alps now. The problem for us is that, again, we were entirely dominated by latency. And these latencies meant that the latency were mostly spent when we're invoking new kernels. So we're spending too much time waiting for the actual computations to start. Then NVIDIA came up with CUDA graphs and everything, and then we could basically have complete an entire schedule and then start the schedule at the start of each step or even for multiple steps, and then throw up all the kernels at once and have all the synchronization working directly on the GPU. This was a miracle the first time it happened. This looks nice, small, and clean, but that's because it's one GPU. The second you move this to just 2 GPUs, I'm not going to say that it can look like a nightmare. It is a bit of a nightmare to code this, but the performance you get out of it is amazing. These small, if you see this small, the magenta, horizontal magenta, these are the kernel launches. And instead of having those spread out all across the time step, they are now all at the beginning for the time steps. So this just means that we can stream everything through and we speed things up by a factor of 2 or 3. We spent 2.5 years implementing this together with NVIDIA. And I'm going to show you some performance numbers. The only problem is that NVIDIA is a large company. And while 2 of their staff was busy helping us implement CUDA graphs, their driver team was also busy improving the driver latency. So over the last 2-3 years, the driver latency has now decreased so much that you don't really need CUDA graphs anymore. And I'm not sure if I'm going to strangle them or I'm going to thank them. But if you're in this situation, you likely don't need CUDA graphs today. Why is this important? Well, you just have one of the largest machines in the world that are designed exactly this way. Alps is not a GPU machine. It's a machine that has an amazing throughput-focused device, the Hopper chip on every card. But at the other part of the super chip is a latency-optimized device, the Grace chip. And you want to use both of them, not because one of them is better than the other, but they're good at different types of algorithms. And if you're really lucky, you might find a way that you can use both of them in parallel, because those 72 CPUs on the ARM core, they're quite nice for anything that's random access. So I always used to boast about GROMACS, and it's so beautiful when we have single node performance and everything, and then it comes the scaling performance, and in particular scaling on GPUs, and it was so embarrassing. This is no longer embarrassing. So the STMV, it's a 1 million particle system. Both GROMACS and other codes, we used to struggle to go beyond 4 GPUs here. And my problem here is that this is one of my research engineers, Szilard Pál, who is very conservative, and I tell anybody in sales should put the number of GPUs on the x-axis, but he insists on putting the number of nodes on the x-axis. So you need to multiply that by 4. So with direct GPU communication and full 3D FFTs here, we scale this system to 64 GPUs quite efficiently, which is pretty neat. And for a larger system, we scale up to 256 GPUs. A single simulation. This is not ensembles or anything. This is a single simulation, and if you look at the performance counts there, these are syncing something like 10,000 times per second. Now, if you have more, I was about to say more money than sense, if you have a lot of money, and if you're buying the state-of-the-art machine, the one type of system that's even more, possibly even more expensive than ALPS today is so-called multi-node NVLink. So the multi-node NVLink systems these are really machines designed to do AI, so that you have fast NVLink communication within each node of 4 GPUs, but then you also have NV-node connections between 18 such nodes. So you have this super fast NVLink communication, low latency network sharing 72 GPUs. Normally, these are probably a factor 3 more expensive than normal Grace Hopper systems, and nobody in the right mind would buy these to do anything but AI. Or maybe one should, because these scale quite nice with simulations too, with NVIDIA's new code. And this is also what I don't necessarily think that NVIDIA has any hidden plan, but everyone in the companies knows the general direction they're moving in. And I'm exceptionally impressed with their ability to work with all their partners and everything. So much of the work that they spent the last 5-10 years of helping us with has, of course, been in preparation for this type of system. So I'm not sure if you saw the previous slide. Now, the previous slide here, we scaled up to roughly, well, say just under 200 nanoseconds per day. And here we're at over 400 nanoseconds per day. And this is Grace Blackwell 200s. Probably not quite worth it if the machine is a factor 3 more expensive, but it's getting there. And the scaling here is not quite as good yet. So here we scale down to something like 25,000 particles per GPU, which again, it's just absurd that when I was a student, that's how far we would scale at the very best case on CPUs. And now we scale that well on GPUs too. And this, again, it's been a tour de force and a ton of people doing insanely good work here. Now, we've, of course, gotten a lot of impact from this. And this slide is, of course, part of GROMACS. We're getting 10,000 citations per year here, 1 every 30 minutes or so. My reason for having this slide is not GROMACS. My reason for having this slide is software in general. This goes into OpenChami. It goes into a whole lot of the efforts we're seeing both in Switzerland and Sweden porting codes over to GPUs. And I would argue it goes particularly for AI. And AI is amazing in some ways, but I worry a little bit that we're seeing so many groups that every year they come back and want to train a new AI model. But if you don't have a plan for what you're going to do with this model next year, who will use your model? Why will anybody else ever cite your model? Will they use it in their papers? If you don't have an answer to that, in all likelihood, nobody will ever use your AI model. Now, you could argue that's not the end of the world. The problem with AI, though, is that the training of AI is so filthy expensive that the only reason for ever doing AI is that if we plan to do orders of more inference than training. If you're using a massive AI training, say in quantum, to replace quantum chemistry, if we're only going to use this once, then it's likely better to solve the problem with quantum chemistry. It only makes sense if you're replacing 100 papers with that AI model. So if you as a researcher want to have impact for this, and I wish that this was a cunning plan that we had 10 years ago in GROMACS, it wasn't. We were students with way too much time and we thought it was fun coding and this was always a side project and we enjoyed working with users. But in hindsight, I think focusing on what other people need is what's created impact for us here. And then of course, 10 years later, we attract substantial funding for it. I think OpenChami is getting there. And I think it's a great example. You're not doing this just for HP. You're having Dell there. I'm very pleased to see NVIDIA. And I'm just trying to get Bull on board. By Sunday, once you have a landscape for this where everyone sees that this is useful to them, that they can use this, they can have some influence, they can adapt this, they can take the software and do everything they want with it, at some point you will start to create a community here. Now, that's not necessarily a guarantee. But what I like what I see, for instance, in OpenChami. I see this openness that they want other people to use it. And I do say we do see that in a number of the AI models too. I think AlphaFold is one great example. It's not just 1 or 2 papers and a Nobel Prize and then they're abandoning it. DeepMind has been quite good about helping people getting impact and making sure that others can use it. And that is why you're seeing massive uptake on it. And that brings me to the second part of my talk here. Now, working with GPUs is kind of fun. And if you're a really good gamer, that I'm the second heaviest GPU user in my family. Or rather, I use many GPUs, but not the fanciest ones. Those are reserved for my son. You know, in games, you need 60 or 100 frames per second, and then you're happy. The problem with our type of simulations is that we're kind of doing 26,000 frames per second, which is cool to boast about and everything, but we're hitting some pretty difficult brick walls here. We're not going to be able to scale this up an order of magnitude. I doubt we're going to be able to scale this up a factor of 5. It's simply, we're not going to get to those frequencies. Now, that's possibly horrible, but you could also argue that if we accept that, that leads to some dire consequences that we will need to find other solutions for. MD simulations are super cool, and we've been able to do some things with it. But if we're not going to get these simulations significantly faster, you basically end up in this problem. Imagine that our proteins are birds or something, and if I'm going to do an MD simulation of a bird, the equivalent we do is roughly this. I know, you learned so much about bird flight here, right? And that's the problem. Simulations are stuck on a microsecond or something. And my generation, so many of us benefited from being able to benefit from computers becoming orders of magnitude faster. But this will, of course, not work if the computers don't keep getting faster. And here I rely on lower latency, not just higher throughput. So to get around that, what many of us have been doing is trying to move to, instead of relying on one simulation, doing many, many simulations. And in the interest of time, I'm going to work through this a little quicker. If you can't do everything in a long simulation, one obvious observation here is that if you're studying a large molecular system, this system, a channel for instance, might spend a ton of time rattling around in a closed state, then it makes a quick transition to another state, and then it's rattling around in that state. But that waiting time, we could do that in parallel. Imagine I have an open and a closed bassinet here. If I just start many simulations in each of these states, I might start to see transitions between them. And you could even do better than that. Instead of just starting in each basin here, you can start, if I just have systems of, for instance, a channel in 2 states, I can interpolate this and start hundreds of simulations going all the way between those things. And divine inspiration is pretty much good here to start with. I just need many starting points. If they're completely unrealistic, I will see that in sampling. And then you start hundreds of simulations, each running a few GPUs in parallel, and you're using maybe 6 months of computing time on 100 GPUs, insanely expensive computationally. And as long as you get some sort of statistical overlap between these simulations, I can throw a lot of statistical mechanics math on these and then reconstruct energy landscapes. And in the interest of time, and since you're in computer science, we were ecstatic about this because we could actually, for the first time ever, explain with computer simulation what's actually happening in experiments and why channels open under some conditions. We can do this even better with modern channels with 3 states, and I'm going to show you in a small movie there. So remember that I said that simulations are normally in the microsecond range. Have a look at the counter up there. This is a movie that I've essentially stitched back using statistical mechanics methods. And the landscape you see on the left are all these low dimensional projection on different states here. And if we start the timer now, so that this is already 50 microseconds for gigantic systems. And it's a full simulation with water, lipids, and everything around it. We already completed a first cycle here in some 150 microseconds. No individual simulation here is longer than 5 microseconds. Not only that, the simulations, we were able to identify intermediate states that were then produced experimentally a year after this paper. So there are so many cool things here biologically. And in particular that I can actually visualize and simulate things covering an entire millisecond. Now this is both cool and a horrible failure. The problem with this, the cool aspect is, sure, I can determine all the kinetics here, and you can make lots of arguments that these timescales are right. But since we're not in biology here, I'm not going to go into details about it. The problem is that this takes 6 months on something that's 10% of Alps. This is not sustainable. There is no way we can do this with research in general and then just hoping to improve a factor 2 at the time. No other scientific studies are worth these costs. So the way we do simulations, it's not sustainable. This needs to be orders of magnitude cheaper, and we're not going to get orders of magnitude improvements just from traditional simulations, which sucks. So maybe we should try to revisit this challenge with AI. Can we do something completely different? Well, I was skeptic. The main thing that changed me, we had determined the number of structures of a human receptor in your eye, and then 2 months after this, AlphaFold 3 came out. And just for fun, I tried to let's put the sequence into AlphaFold and see what's happening, see if they're equally good. And it was scary. Forget about the coloring here, but basically, maybe I had a few more residues on the inside, but apart from that, AlphaFold 3 got every single aspect of the structure right. And I can kind of see why some of my experimental friends are scared to death that the computers are eating their lunch. And this was so good that we started thinking, can't AlphaFold try to determine some of these intermediate structures too? Well, maybe. There have been a number of papers that argue that AlphaFold might be able to do it. And the reason for that is that AlphaFold relies heavily on 2 stages. First, you're using multiple sequence alignments where we're assembling many sequences to get some diversity. And then we're throwing the big AI step on this and just generating structures. And what you can do is that if we deliberately perturb or subsample the multiple sequence alignments here, I basically screw up AlphaFold. That does not look good, but screwing up can be good at some point. So if we're, now we start to move there. If I take my proteins here on the right, on the left, some of those predictions will be completely horrible. And now the movie started, and it's to see all the blue dots from the start there. They would be completely across those low-dimensional projected landscapes. But if I start to apply quality thresholds here, do you see what's remaining at the end? Somewhere there. The structures we have remaining at the end correspond quite nicely to some sort of structural transition here. Now, the problem here is, of course, I can't select a completely arbitrary cutoff. But AlphaFold is not just good at the very end. If I was to create one structure, it would likely just create a closed one. But if I'm just asking AlphaFold to create many structures, sample the conformational space, it's quite good at doing that too. In fact, AlphaFold is likely far better than molecular dynamics simulations at just sampling the conformational space. The way, and I'm not going to go into too much experimental details here, but you can combine this with experimental data. And by combining this with experimental data, we basically find a way to decide where we're going to put this quality threshold, so that instead of just blindly filtering those blue dots, I filter away the blue dots that are not compatible with low-dimensional experimental data. This can be small-angle neutron scattering or small-angle X-ray scattering. There are a number of relatively cheap experimental methods that can't determine the entire structure, but it can show 2 alternative different states. So I had a student who hardly had any experience of AI. He started doing this. It took him a few months to get up to speed. And the whole point here, he is not retraining an AI. He's taking AlphaFold, slightly adapting the inference step, which is orders of magnitude easier than retraining the AI. And it comes back to these things that we all want to train an AI because there is prestige in training an AI. And I think that's bad. Don't go there. That it's so much easier to just do inference. The vast amount of users in HPC centers, they don't write their own codes to do quantum chemistry or molecular dynamics simulation. We're more than happy to pick somebody else's code. And the equivalent of that is AI, is that you don't need to redo the training. Do the inference and use a model that's already trained or just adapted a bit. So Samuel did this. And basically, we're using these Markov states models that we already had before. They're the ground truth here, but we're not training on them, but we can compare to that. And if we're now using these small angle neutron scattering data, and let's pretend that we don't know anything about the structure. AlphaFold 3 was trained prior to the existence of these structures, so we have not included them in the training data. And then, as an experimentalist, I know that there are two states, but let's assume that I don't know anything about the structures. And then we're trying, based on this two type of experimental data, which ones of these AlphaFold models, if I'm forcing AlphaFold, all these structures generated, now calculate, well, do the forward model and calculate what are the expected, for instance, neutron scattering curves here or X-ray scattering curves, and then place this along a low-dimensional projection. What is the most important difference between these? And then divide this into two clusters. I get this red and the blue structures here. And if I plot this on top of this structural data, you see that they correspond quite nicely to my local minima. But I have not used the structural data in any way whatsoever. In fact, if I tell these AlphaFold models to just make one prediction about an open state, it's going to be the blue one, and one prediction about a closed state, it's going to be the red one. They're not perfectly on top of my local minima. On the other hand, I'm not sure, it could be shortcomings on the simulation models. They're not the absolute experimental ground truth. And the models we predict from these AI models are pretty darn good. Not perfect, but they're certainly good enough that if I wear my experimental hat, they can explain how this particular molecule opens and closes. The difference here is that once you develop this takes about 1 hour on a workstation with 2 GPUs. And it was about 12 months between these two studies. So instead of using 100 GPUs for 6 months, this is on the level where you hardly even need a compute center for it. And this is scary. This is the type of leap I have never, ever seen in my generation. Sure, it requires you to reformulate your scientific problem a bit. You can't just push a button and tune it. But to me, this is, I'm not stupid, we're going to keep developing GROMACs, right? But I think this is so obvious going to be what fuels all the drive going forward in science. And these are methods that will be able to benefit from increasingly lower precision tensor units, the increased bandwidth and everything. It's methods where I can sample in theory, I could sample 10 million GPUs in parallel. I don't have this iterative approach where step 4 depends on the result of step 3. So this is not just a model that is more efficient today, but it's a model that has legs and will be able to benefit from the hardware going forward. And then you can start thinking, can AI methods predict the conformational landscapes in general? Not just for one particular random. And I think they can. Samuel continued to do this with a number of different methods. And in parallel, we also saw Frank Noé at Microsoft Research. They specifically designed a network to not predict one single state, but really predict the Boltzmann distribution of states of an arbitrary molecule. This is not to criticize Frank. His model is amazing, but it tells us something about how fast AI development is, because their method was trained prior to AlphaFold 3. And once AlphaFold 3 combined with a few of these methods to just perturb the multiple sequence alignments, actually perform better than these dedicated methods. And that is what's so brutal with the AI space, right? 6 months is an eternity. So any method that's 6 months newer will likely kill everything from last year. In this particular case, the BioMU method is slightly worse, but if there is anything I want to point out, all these methods are so good that I don't even think the molecular dynamics simulations are competitive anymore, apart from special cases calculating free energies or so. And they are able to discover completely new states that the methods have not been trained on. So these black crosses you see there, those are structures that appeared after the training of AlphaFold 3. And you see that all the blue dots, all the green dots on the top right there that we're starting from, they are able to sample structures really close to them. So can we bring this back in any way in simulation? Well, yes, we can. So both in Sweden and CSCS, the one big area where AI is heavily used is to train neural network potentials in simulations. And we have this in GROMACS since a few months. In general, if you're like me and doing molecular dynamics simulation, I care about sampling. And the price I pay for caring about sampling is that I have to give up accuracy. So I can do 30,000 iterations per second here, but there is absolutely no quantum chemistry. I can't make or break bonds, and there are certainly many areas getting below, say, 2 kilojoule per mole accuracy or so is likely not going to work. Now, in the other regime here, you have quantum mechanics. Quantum mechanics is amazing. You can get a perfect answer to your problem, provided that your problem consists of a single electron. Anything more complicated than a single electron, you have to start making some sort of simplifications. But in theory, you can get extremely accurate answers, but it can, of course, take minutes or hours per confirmation, so we can't sample as many states. And this means that there is, in principle, a fertile ground in between here that both we and others have historically explored with so-called QMMM methods, that it's ideally the best of both worlds. You have a region in the center where we have quantum accuracy, and then just a molecular mechanics shell around it. The price is usually that you're stuck on time scales that corresponds to the quantum region. Now, the obvious way to do this is to replace our traditional, the simplified Lipson-style potentials with neural networks. And that works quite well. So GROMACS, as so many other codes, can now do this. We're using a local chemical environment within a certain radius or something. And in that local part of the scheme, we handle everything with the neural network trained on quantum chemistry data. Based on the positions of the atoms in this, the red and orange sphere there, we hand over that to a neural network in PyTorch. And then hopefully PyTorch sends us a potential energy and forces back through backpropagation to GROMACS. And then I use this, well, you can use it in training first to minimize the lost data, and then we take this output and feed it into a molecular simulation. Now, this both works and doesn't work. Actually, it does work in GROMACS, and it works about as well in GROMACS as in all other codes. The problem is that it's slow. And this is slow because PyTorch inference is probably a factor 20 slower than one molecular dynamics time step in GROMACS. Ideally, there are ways around this, and I'm going to come back to that in a second. The cool thing is accuracy here. The accuracy is really good. We get below 1 kilojoule per mole accuracy. We can do this with free energy calculations. We get better data for proteins. I don't think this is ready yet to replace traditional molecular dynamic simulations, but again, on the biomolecular side, our entire field is coming from the field that we're sampling limited. And if we're limited by sampling, it's not a good start to make the simulation 20 times slower. But anybody working with QMMM methods, or in particular material science or so, these methods have legs. Now, the problem with this is that the performance sucks. And that's both good and bad. The problem is libtorch. If you start to make some sort of analysis of this, that it's easy to think deep neural networks, of course, means that there are many layers to this and we have to go through many iterations, right? And anytime you tell NVIDIA that you want lower latency, they start to sigh and say, these devices are meant for throughput, not low latency. Now, having said that, then they go back and they come back a year later and they have improved the latency, so keep complaining. That's the only way they will improve. If you actually start to profile this, it turns out that libtorch is a giant black hole of latency and the GPU's waiting. And this is not unique to GROMACS. So virtually right now, all these codes use libtorch as a magic black box to do the inference, which is also good because it means that you don't have to be a genius and implement all the AI. You can just use libtorch for it. The problem is that of this time step you're seeing here, that the vast majority of time, the GPU is idle. And now, had this been my local code, I think I would have forgiven myself. But this is kind of the most widely used code in the industry, where NVIDIA and AMD and everyone probably have 100 people full-time trying to improve the performance of libtorch because it's part of so many procurement benchmarks. And this is an area where you can likely improve things by a factor 2 or 3 if you just look into it. It's not that these engineers are stupid or anything, but there are so many different execution paths in these codes that for a given problem, many of us will likely have to start going into details and fixing the PyTorch internals. And what's even worse for GROMACS, what we're considering doing in GROMACS right now is taking the weights and re-implementing the inference ourselves. Because that means that we also get rid of the entire step of having to call libtorch in every step. We can use our own domain decomposition or so. So I'm confident would be a strong word. I have hopes that we might be able to shave off 1 order of magnitude in the performance here. So that, and in that case, neural network force fields would only be like a factor 2 or so behind classical force fields. And when that happens, I think I would give up classical force fields because it's the increased accuracy is worth a factor 2. It's not worth losing a factor 20. So I think we're having, I promised to have a few minutes at the end for some questions here, but if I'm going to make some concluding remarks here, I think the single most important lesson here is that AI is here. You have 2 choices. Either you can let it eat your lunch or make sure to use AI to drive your career. And I've gone for the latter. The important thing, both those of you who are users or if you're supporting users, AI does not have to be difficult. Sure, Samuel he's a pretty smart student, but a pretty smart student, it took him 1 month without any prior AI experience to get up to speed here, because you don't need to retrain transformer. You don't need to redevelop a model, and you certainly don't need to retrain things yourself. Tune the inference, and you can get a ton of impact for that. Generative AI in general, AlphaFold is just one, it's insanely good. Call it a model generator, hypothesis generator. What you could argue, what we traditionally do in sampling, in normal simulations. The problem is that the results are bad. And in my case, when I say bad, it's if I ask this AI to generate 1 million conformations, it's not going to be a Boltzmann distribution. I will not have a proper weighting of energies. But here's the thing. If I have 1 million conformations, I'm really good at calculating energies. And I can calculate that in theory on 1 million GPUs in parallel. And when I have calculated the energies with a more accurate method, I can reweight these structures and get a proper distribution. So anytime you have some sort of subsequent step where you can correct these fancy, let the AI be your crazy hypothesis generator, and then just correct it, and we make sure that we get more accurate results better. The big problem here, and that's, again, not to blast anybody, AI has a significant, and now I'm speaking as an application, AI has a significant hype problem. And I don't think people are not lying, but people in pure AI, my hunch, which might be wrong, is that to get a chance to have a significant career, right, you need to have your papers published in EuroIPS. Given the competition, you will only have a paper in your IPS if your result is groundbreaking, world-leading, it's a complete revolution. And therefore, every paper submitted to your IPS describes results as groundbreaking, world-leading, completely replacing all previous methods. And again, this is nobody's fault. It's not that people are misrepresenting their results, but there is this risk of we're fooling ourselves a bit. We're not doing the hard tests. And then we're frequently seeing that when we're subjecting it to critical evaluations later. They're good, but they're not quite as good as one might have believed from those papers. Now, having said that, the important thing is speed of improvement. Like 6 months, and that anything that we worried about 6 months ago, it's not going to be a problem next year. And I so wish that that was the case for traditional simulations, right? And that's why I so see the power here. Now, this might sound like I would advocate that we're going to stop doing everything we're doing and then switch entirely to AI. I wouldn't go quite that far. I still think traditional HPC has a role. We care way more about accuracy than AI does. Many of the hallucinations or so that the various language models do, we would never accept that in HPC. Our quality standards are high, and I think it's our job to keep pushing these quality standards, in particular on AI. But I definitely not just see a role, I think we need to embrace AI and increasingly use models where the things that are the major bottlenecks for us today, can we replace that major bottleneck with AI while still keeping the core of the physical problem. So in my case, I want my Boltzmann distributions. I'm going to keep my equations and I will keep correcting it. But if I can let AI generate 1 billion structures instead of iteratively using Newton's equations of motion to generate 1 billion conformations, I think that's a super win for me. And that gets me to this last point, that if you're an AI developer or if you're training models, if you want impact from this rather than just burning cycles, you need to have a strategy. How will other people use your tool? Not because it's for the best of mankind or everything. You will not have scientific impact for this unless somebody else will voluntarily use your AI method. And on my side, since I'm not the core AI expert here, as long as you have a really good AI tool, I would love to use it and give you impact. I think we have like 5 minutes remaining for a question that this would not have happened without 3 amazing people in Stockholm, Berk Hess, my faculty colleague, and then Szilard Pál and Andrei Alexenko. They're the Eastern Europeans that think that any code sucks, but they worked on this for 15 years, and they are intolerant and impatient with any code that's not perfect, including my commits. But they, together with a corresponding team of 2-3 people from NVIDIA here, in particular Alan Gray and Mahesh Doyade, the thing that they've done together when they work 5 or 10 years is amazing. And that's the other strong. Don't go for the fast wins. Find these collaborations or work together for 10 years, because that's really when you're going to accelerate things by 1 or 2 orders of magnitude. And with that, I would like to thank you for your attention. I'd be happy to take any questions.
Thank you, Erik. 1 or 2. Okay. Wow, people are shy today.
Thank you for the presentation. So in one of your slides, you showed the performance between the H200 and the new NVIDIA cluster with NVLink. And the numbers at the earliest stage. And you mentioned the cost as a 3 times. From a performance point of view, if we compare performance to cost, would be a valid solution, and does it make sense?
There.
Yes.
Yeah.
So I'm comparing the blue one with the red one. And
yes. This shows the power of Grace Hopper. Or yes, Blackwell in this case. Blackwell is not that. I would actually argue that if you look at the lower one here, Blackwell is not that much faster than Hopper for our type of simulations. The key advantage here is, because again, we employ heterogeneous acceleration. So we love having this, a really powerful CPU, and the Grace chip is quite nice, but also very low latency and high bandwidth communication between the CPU and the GPU. That's the main difference from blue to red here. Not that Blackwell is better than Hopper. It is for AI, but for we're doing normal FP32 here.
It will not make sense. Okay. So scaling, what about scaling? Do you see that might continue in this direction? Because I know that we could go up to 72 GPUs maybe, or a little bit more. How do you expect that?
It does. And again, Szilard and Alan, they keep working on this. One challenge with, when you're looking at small system, right, and the FFT, 64 has some very nice properties in FFTs, so 72 is slightly more complicated to work with. In principle, yes, it scales to 72 too, and I think we have reasonably good hopes. As they go up to 144, et cetera, in the next generation, we will be able to keep up with this. And right now, of course, NVIDIA is charging you a lot because this is new. I don't think that this type of networks is inherently that much more expensive than Slingshot or anything. So maybe the future for HPC is that we might have to accept that there are these islands of, let's say, 72 or 144 GPUs. Scaling beyond such an island is not going to be realistic, at least for us.
Yeah. One more question?
So Erik, thanks for the nice presentation. You started out showing the patient, that you hope to revive from ITER. And in Switzerland, we have companies like Novartis and Roche that still have similar questions. And simulation is just the beginning of their pipeline, and they have to answer questions on toxicology, and you know much better than I do. How do you think will AI bridge the full thing, from the problem to, for example, drugs? Do you see some advances there?
Yes, and I would actually, this is arguably one of the areas where AI is really good, right? Because it can take, we're working very close with colleagues at AstraZeneca, and one of their key things that they keep, any idiot can design a binder. That's not hard. The problem is ADME and tox, and that's where most drug fails. And the cool thing with AI can do better. First, it can design drugs that will pass all the ADME and tox steps. You can design drugs that will be easy to manufacture, and you can consider patentability. To make sure to design a drug that I can actually get a patent for, and it's going to be difficult for somebody else to work around my patent protection. And if you're running a pharma company, all these steps are, of course, imperative. We are going to see that, but pharma is also a slow business, right? It takes 10 years from the early discovery phases until you start seeing things on the market. It's just the last 2 years, it's actually a drug targeting one of these receptors. One of the first drugs against postpartum depression. It's really cool because David Shaw's company did simulations on it, and they had part of the IP of the drug because they used simulations to develop it. That's so science fiction today. Wait a decade and you're going to see a ton of drugs that were developed with AI.
Thank you.
Okay, thank you, Erik.
Thank you.